Hello, everyone. So this is part 2 of the lecture series on using the simple algorithm for an unstructured mesh. So if you recall, I mentioned this last time that to be able to follow these lectures, you should first look at the lectures on unstructured mesh finite volume method, and also the lectures on using the simple algorithm for a nice collocated, a Cartesian mesh, structured Cartesian mesh. So these are the two references to that. And of course, you also need to watch part 1 of this lecture series, which I posted a short while ago. So let's get back to where we were. So last time we essentially did part 1, which was this block right here on top, where we solved the momentum equation right here. And today we are going to do this part here where once we have solved the momentum equations, as you know, we get the u hat and v hat, the predicted velocities. And then using those predicted velocities, we first have to calculate phase velocities. And this is where the so-called pressure-weighted interpolation method comes in. And then using the phase velocities, we compute the mass imbalance, which goes in as a source term into the pressure correction equation. So that's what we are going to discuss today, how to use PWIM for an unstructured mesh, and then how to calculate the link coefficients for the pressure correction equation, and finally, how to solve the pressure correction equation. Okay, so what I'm going to do here is actually derive the expressions for the phase velocity using the pressure-weighted interpolation method for an unstructured mesh, and then use those same equations to derive the pressure correction equations. So as you know, the momentum equation in general may be written as this. So as you can see, we are using u hat here because that's the predicted velocity field by the momentum equation. So this equation essentially, as you well know, satisfies momentum conservation, but not necessarily mass conservation, because we are using the pressure from the previous outer iteration in this case. All right. And we have already done this kind of manipulation in the past when we derived, expressions for phase velocity on a nice Cartesian mesh. So same procedure here. We are dividing through by the diagonal and writing this whole equation in explicit form, although that's not necessarily what we intend to do, but it's just a way of writing it. And this is just a picture to show you this is what we are looking at. Here's my cell naught, and adjacent to it, I have another cell, let's call it cell 1, just for derivation purposes, and the phase is denoted by F. So similarly for cell 1, we can write a similar expression. And as before, if you go back to the lecture on the collocated mesh simple algorithm, what we had done there is we had imagined that there is a cell center placed at this point, this blue point here, okay? And we say, well, if we can imagine a cell center located there, we can equivalently, just by induction, write another similar equation as either equation 1 or 2 for the cell center, the imaginary cell center placed at F. And that's what this equation would look like. Now, of course, none of these quantities we know. So we have to make approximations, and some of the approximations we make are as follows. So you can see in this equation here, right here, you see I have this 1 over A naught at F showing up, basically also the volume over A naught showing up in the second term. So here's your volume, and here's your A naught. By the way, these are link coefficients of the momentum equation. I don't have a superscript showing X or Y because they are the same. So we have to approximate that. And what we do is just, again, distance weighted interpolation. So the same weighting functions we use to interpolate any other scalar, we also do that for volume over A naught. Likewise, we have to approximate this term. And this is, again, where we are doing a distance weighted interpolation. So exact same procedure as a structured mesh. All right. Then we substitute equations 1 and 2 into this concocted approximation, equation 5, and that's what gives us this result. And furthermore, if we substitute equations 4 and 6, you can see this is 4, this is 6 right here, and we substitute that into equation 3, which is on the previous slide. This one, the equation for the cell, quote unquote, cell F. If we did that, then we end up with this expression right here. Okay, so this is very similar to what we had for a structured mesh, except you see that I'm not using any finite difference approximations. I've retained the dpdx as dpdx, okay, because we're going to look at that later on. So that's my expression for the phase velocity, the u velocity, okay? And likewise, we can get an expression for the v velocity. Now, I already mentioned in the previous lecture, part 1, that really we do not need to calculate individual phase velocities. What we really need is the mass flux, which is u dot n. So, and that's what I'm showing it here. Okay, so basically this is u nx plus v ny. And once we combine the two expressions, this is what we get, just straightforward algebra. Noting that these are some of our approximations. So for example, the pressure gradient dotted with the surface normal may be written as this. And in fact, this sort of a term appears in this equation that I'm showing you here. So you can clearly see there is a dpdx times nx and a dpdy times ny showing up in the expression, okay? Which is basically nothing but the pressure gradient itself dotted with the surface normal. So using all those algebraic expressions, we can finally write the u dot n, which is what we need to approximate or compute our mass flux, okay, comes out as this. As you can see here again, that this first part is just distance-weighted interpolation of the velocity, okay? And as you know, we have discussed this. We can't just use that because that will give us checkerboard pressure oscillations. But because we are now using pressure-weighted interpolation, we have these additional terms. Okay, again, very similar to what we got for a structured mesh. Here you can see the pressure gradient dotted with the surface normal for cell 0. Here is cell 1. And then we have sort of this, pressure gradient dotted with the surface normal at the face F. Okay, all of this is using now distance-weighted interpolation. Okay, so how do we compute these terms? Well, this guy here multiplied with the volume, so this whole thing here, right there, is nothing but we have already used this kind of expression when we calculated the source term, the pressure source for the momentum equation, which we derived out of the divergence theorem. The same expression we are using here. Okay. So this is nx times the gradient of pressure, and this is ny times the, so this is basically dpdx, and this is dpdy, all right, over volume now. So that's why I have a multiplication by volume on the left-hand side, all right? So it's easy to calculate these guys. And then finally, you get to this part, this last part here. And that, of course, from our unstructured mesh derivations that we've done in the past, we know that, just think of this as phi, some scalar, okay? This will be P1 minus P0 divided by delta, delta being the normal distance, okay? Not the actual distance, but the distance in the direction of the surface normal between these 2 points, okay? So that's your delta, essentially. Again, it's not in the direction directly pointing from 0 to 1, but basically the L vector, which is pointing this way from 0 to 1, dotted with the surface normal. Okay, that's what this delta is. And then you're also going to get some tangential terms. Okay, now one might ask, well, why are you not showing the tangential terms? Are you going to take them into account? The answer is no, I'm not going to take that into account in this final formula. And you might ask why? Wouldn't that create an error? The simple answer to that is that, remember, when we are calculating phase velocity from cell center velocities, which is what we are doing here, everything is an approximation. There is no hard and fast rule that you have to do it a certain way. For example, we could have done just distance-weighted interpolation, but of course we know that that's not going to work. Then we say, well, we do pressure-weighted interpolation, and there is a certain mathematical expression that will result, that will come out of that. However, we don't have to use the exact mathematical expression because, as you understand, when we're calculating something at a phase from two cell center values, the whole process is an interpolation or an approximation. But again, if you want, you can still keep the tangential terms. Only thing is that then that will make your expressions even more complicated. So the next step, of course, again, going back to our algorithm here, is the derivation of the pressure correction equation itself, okay? Because we now need to solve it. So this is the part we just completed, okay? Calculating phase velocities. The next part is the pressure correction equation. So again, we are starting with the same expression, equation 1 from 3 slides ago. And next, what we do is we write the same equation with a double hat. And of course, the difference between the single hat and the double hat is that now we are using the latest pressure field, K plus 1. Okay. Again, remember, K is your outer loop iteration index. Okay. So this is previous outer loop iteration. This is current outer loop iteration. All right. So that's the difference. And of course, the double-hatted velocity, as we know, satisfies both mass and momentum conservation. So if we subtract one from the other, then we get this. Now, of course, in the process of doing so, I have also invoked the so-called simple assumption, which means that, as you can see here, if I subtract this and that, I'm going to get a u prime neighbor and this summation showing up as the first term, which we throw away in the simple algorithm. That's one of the fundamental assumptions of the simple algorithm, which is what I've done here. So as a result, what you end up getting is just the pressure gradient term. So this is now your pressure correction, P prime. Okay. And again, this is dP dx times V naught. We use divergence theorem, same expression as before, except we are now applying it to pressure correction instead of pressure. So that's our expression finally for the velocity correction at the cell center. And likewise, you can get the V velocity correction at the cell center, which simply has Ny instead of Nx. All right. Okay. To derive the pressure correction equation, we also need expressions for phase velocity correction. So here is my expression for the phase velocity itself, which I derived a short while ago. And similarly, we can write a double-hatted phase velocity, which again uses K plus 1 instead of K. It's the same expression, except I have K plus 1. We subtract one from the other, make the simple assumption again one more time, and we end up getting this expression here. Okay, again, this as a pressure correction. Likewise, we can get the V velocity phase V velocity correction, which looks like that. Okay. Now, again, I want to emphasize that we don't need to calculate the phase velocities individual components because that's never required in the algorithm. What we need instead is the dotted correction. And the reason for that is because we need to essentially manipulate the continuity equation. So the continuity equation looks like this. And as you know, the double-hatted velocity satisfies the continuity equation. So that's what I have here. Okay, so this is basically saying the sum of the mass fluxes at the various phases is equal to 0. Important to note again is the surface normals must be pointing outwards when from the cell in question, which is cell naught. Okay, so this is summation over the faces of cell naught. And we can decompose that into a u hat plus a u prime being the outer loop correction. Okay, and then rewrite it this way. And so what we get on the right-hand side is basically negative of the mass imbalance, same as what we got for a structured mesh. Okay, so this is just summed, the mass flux is summed over all the faces using the prediction of the momentum equation, which is u hat. And so we have our correction equation, and of course we can write that this u prime dot n as u prime nx plus v prime ny, and we plug in now our expressions that we had right here one slide ago. We plug those in, to this expression here, and this is what we end up getting. Now notice that one of the things we end up getting here is basically a gradient of pressure, because this is dp dx nx plus dp dy ny, or rather p prime. Okay, so that is nothing but gradient of the pressure correction dotted with n. All right, and as I discussed earlier, you can approximate it as this. Okay, now again, there's the question of, well, should we keep the tangential terms or should we not? Here, the argument for neglecting them is this is, remember, this is a pressure correction equation. The pressure corrections go to 0 at convergence. So whether you take the tangential terms into account or not is not going to affect your final solution at all. It may affect convergence, but it's not going to affect your final solution because they are 0 at convergence anyway, because the tangential terms will also involve pressure corrections, which are all 0. All right. So that is the rationale for neglecting them here, that again, this is a correction equation and we can use an altered form of the correction equation because we're simply predicting a correction. So in the end, then after we plug everything in, we get this sort of an equation. And from that, we can then derive the link coefficients for the pressure correction equation. Clearly, you see that there's this P naught term here. Okay, so therefore the diagonal term will be basically a sum over all the faces of this quantity divided by delta F times area. Okay, that's what we have here. And then the off-diagonal term will be the negative of that quantity because this is your off-diagonal pressure. So this is the pressure at the neighbor, or pressure correction at the neighbor, and that's what you get. And the source term, of course, is the negative of the mass imbalance. So that finally concludes our derivation of the pressure correction equation. And this is simple enough to solve. The next thing I'm going to do is actually show you some code where all this is implemented. Okay. All right. So the first thing is the calculation of the phase velocities. Okay. And let me just pull this up so I can bring it up from time to time. Okay. So this is your U velocity and the V velocity. Okay. So you can see here, there's a WF times U naught plus 1 minus WF times U1. That's what's the interpolated, the distance weighted interpolated velocity is. And then there are all these pressure gradient terms that need to be taken into account. Okay, which is exactly what I'm doing here. So first thing I'm saying is, well, I need to calculate the phase velocity at all faces. So this is a loop over all faces. Okay, right there. And then we are saying, well, if it's a boundary phase, I'm going to simply skip, because at boundary phases, okay, the velocities are already known. I don't need to compute them. They are either 0 or the lid velocity for the example that we are considering. Okay, so those are known. We don't need to touch them. Then we get to interior phases, and the interior phases, we have two cells. Okay, so this is the link from phase to cell connectivity, which gives me the cell index of cell 1 and cell 2. So here, instead of naught and 1, I'm using 1 and 2 in the code, just to make things clear. Okay, so this is the interpolated velocity, as you can see. Okay, X component, there's the Y component. All right. And then I'm also dotting it because ultimately my goal is to calculate the mass flux. All right. I'm not going to bother myself with storing individual components. I'm simply going to store the mass flux. So that's why I'm dotting it already with the surface normal. Okay. Then I calculate this dp dx at naught times the volume. Okay. That's what that is. And you can see here, this is using that summation over all the phase pressures. Okay. So this is the phase pressure. This is by the way, the phase pressure has already been calculated beforehand and stored, because the phase pressure was calculated when we calculated the source terms of the momentum equation. So that's already available to us. Okay. And we are simply using that here. Because remember, these expressions have pK. All right. So we don't need to update the pressure. We haven't calculated the pressure in the outer loop yet. So this is still old pressure. It has already been calculated and stored, and I'm simply using it. Okay. And again, note here, I'm using the surface normal times this SN sign, because that's making sure the surface normals are all pointing outwards from the control volume. So that's basically what you see there is this formula right there. That's what we're calculating. Okay. And we are doing this for cell naught as well as for cell 1, which is done here. So the V1, so this is V naught, as you can see, this is V1, etc. Okay. And we are doing both dpdx and dpdy, and then ultimately doing a weighted average, distance weighted average of those. And then finally, we have this other term, this final term, which is this term here, this last term. Okay, right there. Let me just, right there. Okay, that term, the dpdx, which we said would be something like this, the last bottom formula. That's what we are coding in this last part here. So you see it uses the cell center pressures divided by delta. Okay, and again, there is some weighted interpolation of the term in front of it. And then at the end of the day, so at this point, I have V dot N or U dot N in my notes, okay? And I'm multiplying that by the density and the area to get my mass flux. Okay, so this is the mass flux in kgs per second. And that's what I'm finally storing. So once I have these phase velocities, then the next thing we want to do is actually, the next thing we want to do is actually calculate the link coefficients and the sources for the pressure equation. So the source is very straightforward. You see, I'm saying calculating source term due to mass imbalance. All we are doing is we have already just calculated the m dot f. I'm multiplying it by the SN sign to make sure surface normals are all pointing outwards. Okay, by the way, this already contains multiplication by the surface normal. Here, I'm just flipping the surface normal if necessary by multiplying by that. Okay, and then summing it up, that gives my source term for the pressure equation. Okay, and then I want to calculate my link coefficients. This is very similar to what we did for the momentum equation. I loop over all cells and I set my diagonal to 0 and I set my off diagonals to 0. So this is where I'm looping over all the faces of the cell. Okay, and setting the neighboring coefficients to 0. If it's a boundary face, I skip because the U is 0. So there is no contribution to the pressure correction equation from boundary faces. They're Dirichlet boundary conditions. And then I figure out which is my neighboring cell. It's the same logic we are using as before. Basically, we're saying if the surface normal was already pointing out, then the neighboring cell is cell 2. If the surface normal was pointing in, then the neighboring cell is cell 1. And then finally, I'm calculating my my AP. Of course, I'm summing up because as you can see here in this expression, there's a summation over all the faces, okay, for my diagonal. And for my off diagonal is simply the negative of that term. So that's what we're doing here. We're summing over all the faces. And again, there's a distance weighted interpolation, as you can see in this formula also. There's a distance weighted interpolation. So that's what's happening here, multiplied by rho times area, divided by delta, and likewise with a negative sign for the off diagonals. So at this point, I have my pressure links, I have my source term, and I'm ready to solve. Now to solve, again, I'm using a simple Gauss-Seidel iteration. One of the important things is that you must set the pressure correction to 0 at the beginning of the pressure solve. So in the outer loop, okay, so suppose you have your first outer loop iteration, you solve the pressure correction equation, okay? So that array pressure correction has been populated with some numbers. When you go into the next outer loop, you don't want to use those numbers. The reason being that at convergence, the pressure correction is 0 already, okay? That's what it should be. So therefore, it is advisable to actually start with the correct answer, which is 0. Rather than use values from the previous outer iteration, because those values may not be meaningful in the second iteration. Many a time, students come to me saying their code is not converging, and this is one of the classic problems. They did not set the pressure correction to 0 in the outer loop. You must do that to get stable convergence, okay? So you do that, then you call your link coefficients and sources, which is the function or subroutine that I just showed you. And so now you have everything ready at your fingertips. Here, I'm doing a very simple Gauss-Seidel iteration. So all I'm doing is I'm marching cell to cell or point by point, figuring out what the neighbor is, and then I'm computing the sum of the off diagonals. Okay, so this is the neighbor times the pressure correction of the neighboring cell. And then finally, I'm saying my actual correction at the cell center is the source minus the sum of the off diagonals, which I've popped over to the essentially to the right-hand side, divided by the diagonal. So that's my pressure correction. Okay. And of course, I need to also monitor the residual. So I'm computing the residual also. And the residual is the whole equation. So the source, and then we already had the off diagonals. Here, what we are doing is also subtracting out the A naught times P naught prime. Okay, and then of course monitoring this also. So that's what the solver for the pressure correction equation is. It's straightforward Gauss-Seidel, nothing fancy there. So that brings us to, if we go back to the algorithm, we are at the end of this here. So we have solved the pressure correction equation. So next part of the lecture, what I'm going to talk about is how to correct the velocities and pressures. We have already derived the expressions for those. It's just a simple question of implementing it in a code. I'll show you some sample code for that. And then we will talk about the results of this driven cavity problem in a ground bus. Okay, so we'll go over some studies on how the different parameters affect the convergence, what the results look like, and so on. So that would be part 3. So thank you again, and I look forward to seeing you again for part 3.